And he was able to show that, two trains passing each other, the clocks are going to be running faster on one than another, and there's dilation of whatever. And it turns out the whole world can be described in terms of relativity. Until that next smart guy comes along. Okay? But while it was true, right? I mean, while we were using F equals ma, everything was F equals ma. And when we discovered that E equals mc squared, which is actually just an aspect of relativity, that's what's true, right? Ancient Greeks believed that everything chemical in the world could be made of 4 elements: earth, wind, fire, water. And they spent incredible amounts of time describing how your exhalations of breath from your lungs are 90% air and 10% fire. Can't you feel the fire flowing from you? Can you feel it? It's warm, right? And this worked really well for them, and it was very true. And they went to great works to show that this was true for everything until somebody discovered atoms, right? And then they came up with other explanations as to how things are made. And atoms, they were indivisible. That's what the word atom means, right? You can't break an atom. It is lead. It is uranium. It is hydrogen. Until, of course, somebody learned that you could break a both, but there were things inside of there, right? In the same way, in meteorology, we have paradigms. Things we believe, and we believe to be right, but somebody's going to eventually, someday later, show us that that's actually just a very simplified way of looking at things. It's actually much more complicated. In meteorology, some examples of paradigms are things like polar front theory. Okay, now, polar front theory, if you're not familiar with that terminology, this is things like fronts, air masses, cyclogenesis, etc. Lovely idea. It was invented, by the way, in the late 1800s, rather, in Norway. This is when he came up with this whole business. Because we didn't know what fronts were. We couldn't figure out what was this business of temperatures changing. Okay? Now we have this idea. Someday later, someone will figure out a better way to describe things. Okay? Some of you might, for example, be familiar with conveyor belt theory. Is another way of describing the atmosphere that doesn't involve fronts and stuff like that. Another example of a good paradigm in meteorology in general is geostrophic theory, or actually more accurately, quasi-geostrophic theory. If you've taken dynamics, you know all about this. If you took intro, you knew about it. You just didn't know you knew about it. This is things like the pressure gradient force is balanced by the Coriolis force, so winds flow parallel to contours, etc., etc. Okay? It's a lovely explanation. Someone came up with it. Okay? But someday later, it will be surpassed by a different theory. Maybe potential PV theory is kind of a rising theory in meteorology right now. Potential vorticity theory. We will someday replace what we think about how the atmosphere works. And some of these theories don't really work very well in the tropics. How well do you suppose this works in the tropics? Is this a polar front? Does the polar fronts have anything to do with the tropics? No, there's no fronts there, there's no cyclones, there's no air, well, there's air masses in kind of the sense of the word, but that isn't how the tropics work. The tropics work differently. So this doesn't really apply. If you spent your whole life in synoptic meteorology 1 learning how to find fronts, you're going to sit down in one of those charts I just put up on the screen and go like, well, I don't understand. What the hell is this all about? Where's the front? I can't find it. Probably couldn't find it. It's not the secret, but okay. That's because why? Ain't no such thing as fronts, right? It's an idea. If you thought it was hard to find the fronts, you were not missing the point. There's no such thing as a front. A front's not like some piece of paper or wall that's moving through the atmosphere, right? It's just a place where the temperatures are changing. Right? Picture you saw in your intro book, they lied to you. Right? But it certainly did lie to you if you're thinking about tropics, right? There aren't going to be fronts there. How about geostrophic theory, quasi-geostrophic theory? Pressure gradient force balanced by the Coriolis force. Anybody see problems with that in the tropics?
No Coriolis.
Yeah, man, there's whole textbooks about quasi-geostrophic theory. And you can learn all kinds of important things involving vorticity and all kinds of things involving Laplacians of differential advection that's going to make it. We'll have her explain that in one Friday class. Yeah, none of that works in the tropics. People spend their lives learning that stuff, and it doesn't do any good in the tropics. Right? On the other hand, there are paradigms that we use in meteorology that do work, like air parcel theory. Okay. This, again, whether you are a grad student or whether you've only had intro, you know about air parcels. You move them, you lift them, they cool at the dry adiabatic lattice rate, the moist adiabatic lattice rate. Adam, what does an air parcel look like? How big is it? That's telling me we have 5 minutes left, by the way. How big is an air parcel? 0.1. There ain't no such thing, right? Air parcels are an idea, right? I mean, this idea that air parcels are something you can lift, it's going to cool the dragging back lap rate, and it's going to be a different temperature than the air around it. There's no such thing, right? The air that you're looking is the air around you, right? They mix. It's air, right? There's no such thing. We lied to you. Man, we spent so much time in meteorology lying to you. Okay? On the other hand, this theory works just as well in the tropics as it works in mid-latitude. We can sit there with a thermodynamic diagram and we can lift air parcels on the dry back rate until they're saturated, then we can lift them at their moist back rate. It works as well in the tropics as it does in the latitudes. Air parcel theory is definitely one of the ones I'm waiting for us to replace because I think it's such a crap. But anyway, well, it's not so much of a crap, it's just not a very good approximation of that. Anyway, the point is, there are lots of these kind of ideas that we use in meteorology, some of which don't work in the tropics, but do work in the latitudes, and some of them don't really work anywhere. But we use them because they're a way that we wrap our brains around ideas. Here's another one. Oh, I'm going to destroy your faith. You're going to all change your majors after this. Climatology. We all believe in climatology, right? There's an average temperature for August 22nd in Omaha, right? I don't know, let's say an average high temperature of 84 degrees. Is that real? Is it true that the average high temperature in Omaha is 84 degrees? Well, I mean, yeah, the last maybe 30 years, right? Average over the last 10,000 years, you know, back when there was an ice sheet 2 miles deep over here, we got a different number, right? What does that 84 number mean? It probably doesn't mean anything, because if we use the last 10 years instead, maybe we would have gotten 86. And if we use the last 50 years instead, we would have gotten 82. Oh, crap. You mean climatology don't mean anything? Yeah, right, so it's an idea, though. It's a useful idea, right? There is some kind of average temperature. We kind of have an expectation of what late August in Nebraska should look like. It's a useful idea, but in many ways it's just nothing, right? It's kind of making something out of nothing. Okay? It's a useful idea, but it's not true. Okay? We have all kinds of these paradigms in meteorology. The paradigms for tropical meteorology tend to be different. We look for different things in the tropics, like oscillations. This will be where we'll stop after this one right here. Tropics are full of things that we call oscillations. El Nino, the Southern Oscillation. The Madden-Julian Oscillation. You don't ever hear about the Omaha Oscillation. We'll talk more in the third unit, of course, of what is this business with oscillations, but this is something we look for in the tropics. We tend to think in terms of, oh, we're going to look for 7 to 21 day breaks in surges in the monsoon. We don't hear about 7 to 21 day breaks and surges in storm patterns over Nebraska, right? This is something we do in the tropics that we don't do in the latitudes. There's good reasons why we do it, but it's also crap. Okay? So there are these paradigms. Anytime you think about science, this is a whole, worked a lot better when everybody had the history of science class and they're like, oh wait, everything I learned is wrong. Yeah, everything I learned is wrong. Don't worry. We'll fix it. All right. I know we had to move kind of fast today, but we had to get through those notes and do the syllabus stuff. I will send you guys the first chapter of the Buckle textbook, and you have a reading. We'll start off in the class on Friday with a quiz. We'll find them in here until our 11th student shows up. And if you have any questions, I got office hours or whatever. All right? See you later.